Hi, it's Armin Yagini here. I'm a solution architect, and today I would like to provide you with an introduction on microservices in AWS. Microservices architecture are not a completely new approach to software engineering, but rather a combination of various successful and proven concepts, such as agile software development, service-oriented architectures, API-first design, and continuous integration, continuous delivery. In this video, we're going to first describe the different aspects of a highly scalable fault-tolerance microservices architecture, which normally consists of a user interface, microservices implementation, and a data store, and also how to build it on AWS, leveraging the containers technology. We're then going to recommend AWS services for implementing a typical microservices architecture in order to reduce the operational complexity. And finally, we will look at the overall system to discuss the cross-service aspects of the microservices architecture, such as distributed monitoring and auditing, data consistency, and asynchronous communication. Typical monolithic applications are built using different layers: a user interface or UI, a business layer, and a persistence layer. A central idea of a microservices architecture is to split functionalities into cohesive verticals, not by technological layers, but by implementing a specific domain. Basically, by breaking down the monolith into smaller parts and services, we can make them to communicate to each other and perform the specific task that they have been given to do so. Let's have a look at this in more details.
We're going to start by a typical microservices application and architecture in AWS. First, the user interface layer. Modern applications often use JavaScript framework to implement a single-page application that communicates with REST APIs. In AWS, a static web content can be easily served using Amazon S3 and CloudFront. Since clients of microservices are served from the closest edge location and get responses either from a cache or proxy server with the optimized connection to the origin, latencies can be significantly reduced. However, bear in mind, microservices running closer to each other do not benefit from a CDN. In fact, in some cases, this approach might actually produce additional latencies. So a best practice is to implement other caching mechanisms to minimize your latencies.
Next is our microservices layer. Now, bear in mind that as we are going through our typical microservices application implementation, I would like to introduce you to other related AWS services that you can use in your microservices implementation for your organization. That way, you can see the potential benefit of each of them and pick the right one for your architecture.
We often say that APIs are the front door of microservices. By that, we mean that APIs serve as an entry point from the application logic beyond a set of programmatic interfaces, typically a RESTful Web Services API. This API accepts and processes calls from client and might implement functionalities such as traffic management, request filtering, routing, caching, authentication, and authorization. AWS has integrated building blocks that supports the development of microservices. Two popular approaches are using AWS Lambda and Docker containers with AWS Fargate.
With AWS Lambda, you simply upload your code and let Lambda to take care of everything that is required to run and scale the execution based on your actual demand curve.
Lambda supports several programming languages and can be triggered from other AWS services or can be triggered directly from any mobile or web applications. One of the biggest advantages of AWS Lambda is its agility. Lambda allows you to move quickly. You can focus on your business logic because security and scaling are managed by AWS. Also, a very common approach to reduce operational effort for deployment is container-based deployment. Container technologies like Docker have increased in popularity in the last few years due to the benefit like portability, productivity, and efficiency. The learning curve with container can be steep, and you have to think about security fixes for your Docker images and monitoring. Amazon ECS and EKS eliminates the needs to install, operate, and scale your own cluster management infrastructure. With simple API calls, you can launch and stop Docker-enabled applications, query the complete state of your cluster, and access many familiar features such as security group, load balancing, EBS, and IAM roles. Amazon ECS supports container placement strategies and constraint to customize how ECS places and terminates tasks. A task placement constraint is a rule that is considered during the task placement. You can associate attributes, essentially key value pairs, to your container instances and then use a constraint to place tasks based on these attributes. For example, you can use constraints to place certain microservices based on the instance types or capabilities such as GPU-powered instances. In addition to ECS, for those of you that like to run Kubernetes on AWS, Amazon offers EKS. EKS runs up-to-date version of Kubernetes, so you can use all the existing plugins and tooling from the Kubernetes community. Applications running on Amazon EKS are fully compatible with applications running on any standard Kubernetes environments, regardless if it's running on public clouds or your on-prem data center. EKS integrates IAM with Kubernetes, which enables you to register IAM entities with native authentication system in Kubernetes. There is no need to manually set up credentials for authenticating with Kubernetes master. The IAM integration allows you to use IAM to directly authenticate with master itself and provide you access to public endpoints of your Kubernetes master. Also, the Docker images used in Amazon EKS or ECS can be stored in Amazon Elastic Container Registry or ECR, which eliminates the need to operate and scale the infrastructure required to power your container registry. And lastly, AWS Fargate, which is a container management services that allows you to run serverless containers so you don't have to worry about provisioning, configuring, and scaling cluster of VMs to run containers. With Fargate, you no longer need to worry about provisioning enough compute resources for your container applications. Basically, Fargate can launch tens of thousands of containers and easily scale to your most mission-critical applications. Okay, so before we go through our last layer, the data store layer, I would like to introduce you to a really cool and useful service from AWS, the Private Link. AWS Private Link or VPC Endpoint Services is a highly available, scalable technology that enables you to privately connect your VPC to supported AWS services, services hosted by other AWS accounts, and supported AWS Marketplace partner services. When you use a private link, you do not need an internet gateway, NAT device, public IP address, AWS Direct Connect connections, or VPN connections to communicate with other services. Basically, the traffic between your VPC and the services does not leave the Amazon network. This makes the private links a great tool to increase the isolation of microservices architecture. For example, it's possible to create hundreds of VPCs, each hosting and providing a single microservice. Companies can now create services and offer them for sales to other AWS customers through a private connection and without exposing them to the public internet. They can create a service that accepts TCP traffic, host it behind NLB, and then make the service available either directly in AWS or in Marketplace. Okay, so this will bring us to our data store layer. The data store is used to persist data needed by microservices. Popular stores for session data are in-memory caches, such as Memcached or Redis. AWS offers both technologies as part of the managed Amazon Elastic Cache service. Putting a cache between application servers and a database is a common mechanism for reducing the read load on the database, which in return may allow resources to be used to support more writes. Caches will also improve latencies. Relational databases are still very popular to store structured data and business objects. AWS offers 6 different database engines as a managed services via Amazon RDS. Relational databases, however, are not designed for endless scale, which can make it difficult and time-intensive to apply techniques to support a high number of queries. NoSQL databases have been designed to favor scalability, performance, and availability over the consistency of relational databases. One important element of NoSQL databases is that they typically do not enforce a strict schema. Data is distributed over partitions that can be scaled horizontally, and it is retrieved using partition keys. Because individual microservices are designed to do one thing well, they typically have a simplified data model that might be well suited to NoSQL persistence. It is important to understand that NoSQL databases have different access patterns than the relational databases. For example, it's not possible to join tables. If necessary, the logic has to be implemented in the application. You can use Amazon DynamoDB to create a database table that can store and retrieve any amount of data and serve any level of request traffic. DynamoDB delivers single-digit millisecond performance. However, there are certain use cases that require response times in microseconds. DynamoDB Accelerator, or DAX, provides caching capabilities for accessing data. DynamoDB also offers an automatic scaling feature to dynamically adjust output capacity in response to actual traffic. However, there are some cases where capacity planning is difficult or not possible because of the large activity spikes of short duration in your application. For those situations, DynamoDB provides an on-demand option, which offers simple pay-per-request pricing. DynamoDB On Demand is capable of serving thousands of requests per second instantly without capacity planning.
This marks the end of Part 1. The architecture that we have described in Part 1 is already using AWS Managed Services. However, as you have guessed, we still have to manage our Amazon EC2 instances. But don't worry, we can even further reduce the operational efforts needed to run, maintain, and monitor this model by using a fully serverless architecture. If you'd like to find out how, follow me on LinkedIn and stay tuned for Part 2 of this series. Part 2 is going to be purely focused on reducing operational complexities.